is center of mass. Okay, the center of mass. We've actually talked about this concept before. Center of mass, we could define this as the location at which all the mass appears to be located. Okay? And you can model things as if it was located at that point, at that location. So for example, we talked about this when we talked about planets. Right? Where's the center of mass on, let's say, a uniform planet? At the center of the planet. The center of the planet. So when we did our gravity calculations, we didn't measure the distance from surface to surface. We measured from the center to the center, because we can model this as if all the mass was located at each center, right? So assuming all that 10 to the 24th kilograms mass is located at a single point in the middle here. So with the seesaw, we can do the same thing. And you should have done this yesterday, as the very first thing I asked you to do was to do what with your ruler? To balance it out, right? And so you balanced it right here. And if this was a nice uniform ruler, where should that mass, center of mass, be located? Right in the center, right? Right at the 50 point. So I could put my finger here, and putting my finger right here in the middle of the ruler, basically I'm holding up all of the mass as if it was located right here at a single point. Now if I move my finger a little bit one way or the other, what's going to happen? It's going to fall down. And why does it fall? Okay, maybe let's go back. If I go here, so I can assume all the mass is at the center. In reality, it's not though, right? We have mass on this side producing a torque this way. We have mass on this side pushing a torque this way. Well, what's going to be true about those two torques? They're balanced, they're in equilibrium, right? Because they're equal. The mass on this side is equal to the mass on this side, right? The same way I can say, well, there's a mass at the center of mass just pointing down. Well, once I move the fulcrum, now I have more mass on the right. There's going to be a net torque this way because there's less mass here going in the opposite direction. So one of the ways I could model this is say, well, let's do it here. If the center of mass is right here, if I now move this fulcrum over here, let's say some distance, I'll just say 10 centimeters. So there's more mass on this way, this side producing a torque here. There's more mass this way pushing a torque here, less mass pushing a torque here. The net torque obviously is going to go to the right. Well, I could model this as if all the mass was located right here, pushing down, and this should be this distance here, pushing down with a torque in this case, clockwise direction. And so the net torque here of this ruler would be equal to, well, in this case, we'll just call it the mass of the ruler times g times the distance of the center of mass to the fulcrum. Fulcrum to COM. Which in this problem I just gave you would be 10 centimeters, right? So we could say, okay, there's a mass, a torque due to the ruler located right at that center point. Okay, so for example, if we had two masses, we had Dad over here, we had little guy over here. To set this up and solve it, we wouldn't just simply go m1g, like m1g d1 equals m2g d2, because there's a third torque, and the third torque's coming from the ruler. So we'd have to add in, now which side would we add in that third torque? To the right side. So we'd say, okay, plus the mass of the ruler times g, well, what we just did right here, right? Times g times that d ruler. Okay, and so we'd add in that little piece here. So we'd include the center of mass torque. All right?